Okay, bell ringer. Which of the following statements is false? Let's go statement by statement. You can tell me what you think. All right, if two particles collide with each other, if you treat the two particles as a system when using the principle of impulse and momentum, the collision impulse is internal to the system and cancels out. True or false? Why? I hear true. That is true. And in fact, we did this in the class that I'm hoping you watched, but now I'm realizing you might not have watched it yet. So the class that we did over video from last week, that one shows an example where we do exactly this. We treat the two particles that are hitting each other as a system of particles, which means that in the direction of the collision, linear momentum is conserved. So the impulse from one particle hitting the other going this way is equal and opposite to the impulse going this way. So they cancel out within that system of particles. Okay, so this one is true. All right, the impulse created by a body's weight is usually negligible compared to a collision impulse. True or false? Samuel?
It's true because collision impulses are so quick that you can ignore weight.
It's a combination of the time being very short, but also with the impulse, the amplitude of that impulsive force for a collision is just much, much greater than what you'll see with a single constant weight. So yes, so this one is true. Okay, like the principle of work-energy equation, the principle of impulse momentum is a scalar equation. True or false? I heard someone. False. You are correct. That one is the false one. Okay. Principle of work energy is indeed a scalar equation. Energy doesn't really have direction, or the work energy problem doesn't have direction to it. However, impulse and momentum is a vector equation, okay? So we can look at impulse momentum specifically in the x direction or in the y direction or really any other direction. All right, last one, which I sure hope is true. Momentum can simultaneously be conserved in one direction, but not in another. It is true. Okay, it's true because this impulse momentum equation is a vector equation. So we can look only in maybe the x direction is conserved. There's no impulsive forces happening in the x direction. But maybe in the y direction there is. Okay, and so momentum is not conserved in that direction. Okay, so this is true. So the correct answer here would have been C. If you have not watched last class, you need to go on YouTube and watch that class. Yes?
I was going to ask what video was.
It's on our same playlist as all the other video recordings. Yeah? I am recording, thank you. Anything else? Okay. All right, today we're going to look at impact specifically, which we actually started just a little bit of in the last video. Okay, so there are a couple of terms that we're going to talk about when we discuss two things colliding with one another. So we're still talking about particles here. Maybe I'll add that. We're still talking about particles, and so I'm going to draw this diagram of what it looks like when two particles hit each other. So I'm drawing a very zoomed in look at two particles, A and B. And A and B are going to contact each other at this point in the center. All right. Now each of these particles has basically a center. Actually, sorry, I'm going to back up and say, let's be more general here. Let's not just talk particles. Let's pretend these are two bodies hitting each other. Two bodies hitting each other that may have volume. Okay, so two objects, two potatoes, A and B. And I'm drawing their center of mass point G. Those are the first two important things. So we have two different pieces of geometry here that we need to define. And the first is the line of impact. This red dashed line, this is the line that passes through the mass center of the two bodies or particles. Okay, so convince yourself that that is true in this image, that that red dashed line goes through the center of mass point G for both bodies. Given the line of impact, given that line of impact, we now can classify different types of impact into two categories. We can either have central impact or oblique impact. And the difference between these two depends on the velocity of the bodies just before impact. Okay, so a central impact occurs when the direction of motion of the mass centers of the objects directly before impact are along the line of impact. Okay, so the two things that helped us define this term, we looked at the line of impact, which goes between the two centers of mass of the bodies, and we looked at the velocity of these bodies directly before impact. If the velocities line up with the line of impact, we call that a central impact. If they do not line up with the line of impact, so if the velocity is in any other direction than directly in line with the line of impact, we call that an oblique impact. Okay, so when the motion of one or more particles or bodies makes an angle with the line of impact. Okay, so I drew the velocities of these two bodies using black arrows and black dashed lines that go in the direction of those arrows. And you can clearly see that they are not in line with the line of impact or the LOI. Okay, the last little definition I want to give you here is about the plane of contact, which is not entirely necessary for understanding these two types of impact, but we will use it potentially in the upcoming problems. So the plane of impact is always going to be that plane which is perpendicular to the line of impact. So I'll add that down here. Plane of impact. The plane perpendicular to the LOI, or the line of impact. Okay, so now what we're going to do is we're going to go type by type. So first we're going to talk about central impacts, and then we're going to talk about oblique impacts. And there are different strategies for the equations that we should use when analyzing these two types of impacts. And what we're going to find is that central impacts are a little bit easier to handle. Okay, it turns out with a central impact, we can mostly do what we need to do considering only one direction. But with oblique impact, we really need to do some math in one direction and some math in the other direction. Okay, so it gets a little bit more complicated. Yes?
Are we worried about elasticity yet?
We will be, yes. Yep. Okay, so let's talk about a central impact. And this is actually where elasticity comes in. So you're right on track. So with a central impact, we have this kind of process that happens very, very, very quickly. So let's consider two objects that are coming like straight toward each other. So here we can see the center of these two objects is here, and if we were to draw the line of impact, it would be directly along the line of motion of those two objects. So we're doing a central impact, and what we'll see is that those two objects are going to just touch, and then they're going to exchange this tremendous amount of energy that might actually cause these objects to deform. That should make you really uncomfortable, because really early in this class, Dr. Higgins said, we don't deal with objects that deform in this class. And that is still true to some degree. So essentially what we're going to do is we're going to use a principle of basically a coefficient of sorts to help us to describe what happens between point B and point C. But we are not really going to dive in depth into the physics of what happens while these bodies are deforming and undeforming. Okay, so there's kind of like a bridge that helps us to avoid thinking carefully about the deformation phase. Okay, however, when objects are doing a very, very large force over a very short amount of time, there's going to be some deformation that happens. Okay, so there are going to be different types of deformation. So some types of deformation are going to cause a temporary change in shape to the object that is fully restored at the end. And then there are other types of deformation where they're going to essentially crumple and not ever regain their shape. Okay? All right, so we come together, we kiss. They start to deform, they deform together, and then they start to undeform. They start to come back to their original shape, and then after the impact, they could potentially go away from each other, or depending on the velocities beforehand and the masses beforehand, they could go off in a common direction. Okay? So this is what we're dealing with today. And it turns out it's going to draw quite heavily on our last topic. All right, so to write a couple notes here. We can analyze the two-particle system using the conservation of momentum because the impulse caused by the collision cancels. Okay. So why do I say that? It's important that I'm using this term here, the two particle system. When I treat it as two particles, I have the sum of m1 v1 plus the integral from t1 to t2 of f impulsive dt equals the sum of m2 v2. Okay, and when I have all of these summation signs for my system of particles, it means that the impulse felt by one of these particles is equal and opposite to the impulse felt by the other particle, and thus they cancel, meaning that this term here goes to zero, and the resulting equation is what we call the conservation of momentum. So this is momentum, and momentum is the same before and after the collision. Okay, so let's maybe write that in a little more detail. So here we'll say if we have particle A and B, it means that we have MAVA1 plus MBVB1 is equal to MAVA2 plus MBVB2. So this is momentum before impact, and this is momentum after impact. So we will need to use this equation, but it turns out that more often than not, this equation alone is not enough. It's not going to be enough. We'll still have too many unknowns. So there's an additional relationship that we need to talk about that will help us solve problems in this area. And that other relationship is called the coefficient of restitution. So based on material properties, or experimental data, it's possible that we may know what's called the coefficient of restitution. Let's do all caps. And this coefficient of restitution is usually given by this variable E. And here is what E tells us. E is equal to VB2 minus VA2 over VA1 minus VB1. If you want to think at a maybe higher level, you can think about this as being the relative velocity after impact, bless you. Oh, I ran out of room. Over the relative velocity between the two particles or bodies before impact. And E takes a value between zero and one. Okay, so E can have any value between 0 and 1, but it turns out that we have very special names for what's happening if E is exactly equal to 1 and if E is exactly equal to 0. We don't really have a special name for in between, but for perfectly 0 and perfectly 1, we have special names that we'll talk about next. Caesar?
So if it's perfectly 1,
Yep.
that means it doesn't lose any velocity.
It doesn't lose any relative velocity. That's right. There's no energy lost. So that is when the shape of this object, even though it goes through a deformation, it is perfectly restored by the end. Okay, so there's no change in shape after the impact. However, when it is less than 1, it means there has been some energy loss, which usually means that the object has deformed in some way that it's not going to get back. Okay, so let's talk about E equals to 1. Any idea what this is called? You've probably actually heard it before. We call it a perfectly what collision? Elastic, yes. Elastic makes sense, right? When we think about things that are elastic, we can stretch them and stretch them and stretch them, and we let go, they go back to their original shape. Okay, that's exactly what I just described for E equals to 1, right? Our shape is perfectly restored after the impact. Okay, so perfectly elastic collision. And I'm using these words collision and impact the same. I'm using them synonymously. Okay, perfectly elastic impact. E equals to 1. You'll see I have this little diagram here that looks like a bouncy ball. So the bouncy ball, if you start out at one height, this is when E equals to 0. The two bodies stick together. And move with a common velocity after impact. Here, think Play-Doh. Okay, so my diagram here is that we have this Play-Doh ball being dropped, and when it hits the ground, it splats and it stays there. And you'll notice for these two diagrams, I'm actually only drawing one particle. What is the other body that it's impacting? The ground, okay? And so the ground is still both before and after, okay? So when they have a common velocity after impact, that common velocity here is 0. All right, questions before we move on? So if a problem tells you that the two bodies impacting each other have a perfectly elastic impact, what it's telling you is that 1 is equal to VB2 minus VBA over VA1 minus VB1. Did I do that right? I did do that right. Yeah, so be careful with this equation because the subscripts are weird. So you have both 2's on top and both 1's on bottom, but which comes first, B or A, is different from top and bottom. So just be careful with this equation. All right, let's do an example. The 15 megagram, oh my goodness, megagram, tank car A and the 25 megagram freight car B travel toward each other with the velocity shown. If the coefficient of restitution between the bumpers is E equals 0.6, determine the velocity of each car just after collision. So really quickly, let's just prove to ourselves that we are in fact doing a central collision. So I'm going to make a good guess here that the center of mass of these two bodies is somewhere in the center. And if I draw my line of impact, it would be something like this. And then if I draw the velocities of these two things, A is moving this way and B is moving that way. So our velocity lines are perfectly aligned with our line of impact. So we do know for a fact this is a central impact. Okay, as soon as you're able to identify this as a central impact, what I want you to think of doing is conservation of momentum in the direction of motion and coefficient of restitution. Those are the two equations I want you to think of as soon as you're able to identify that what's happening is a central impact. Okay, so let's do that. Let's say, all right, central impact means I'm going to do conservation of momentum in the x direction. So it's the x direction here simply because I drew x in the direction of the line of impact. Okay, so what this means is MAVA1 plus MBVB1 equals MAVA2, bless you, plus MBVB2. All right, do we know the mass of A? Yes. There's not actually a reason to switch to kilograms in this problem, so I'm just going to keep it in these megagrams. So we'll have, let's see, tank car A is 15 megagrams. And do we know the initial velocity? Yep. It looks like it's going in the... okay, sorry. I'm going to draw these as vectors because we do actually need to keep track of what's left and what's right. Okay, so I'm going to draw this. I'm going to say this is a positive 5 meters per second. B is 25 megagrams and is moving minus 7 meters per second. Equals, still 15 is the mass. But the problem is asking me what direction and how fast is it moving afterwards. Similarly, B is still 25 megagrams, but the question is asking me what direction and how fast is it moving afterwards. Okay, so I wasn't lying to you. We still have a problem. We still have a one equation, two unknowns problem. The two unknowns are the two velocities after collision, and I only have one equation. So this is exactly why we need that additional relationship for E. But wonderfully enough, we're given E. So all I need to do is write down that E, which is equal to 0.6 given in the problem, is equal to the equation VB2 minus VA2 over VA1 minus VB1. Okay, let's fill in what we know. We don't know the top line. Yes, ma'am, Leah?
Is it VB minus VA for the numerator and denominator?
It is not. They do switch. If we go back, that's why I startled myself. I said, did I do that right? This is actually true. Brayden? Yeah.
Is it okay to assume that the masses remain the same if it's like
Yes.
plastic?
Yep. In fact, yes, you can always assume the masses remain the same. However, if they become one body, meaning they stick to each other, the total mass is going to be the sum of the two masses. Those are the only two cases we're going to deal with this in this class. Okay? We are never going to deal with like particles breaking off, but in reality, that is absolutely possible. Okay?
Or energy loss due to deformation. Like cars.
The coefficient of restitution takes that into account. But you may, regardless of that, you may assume that the masses stay the same. So the coefficient of restitution takes into account the loss of energy because it takes energy to do that deformation, right? Okay, what do we know here? We don't know anything about the top. That's what we're trying to find. So VB2 minus VA2, that's what the problem's asking for. But we do know the bottom. We know this is VA1 is 5 minus a negative 7. Hooray! 2 equations, 2 unknowns. This makes me happy. All right, so if we rearrange here, this coefficient of restitution should give us 12 times 0.6 plus VA2 equals VB2. And if we plug that VB2 in up here, we'll be able to solve for VA2. Yeah, I'll let you guys plug and chug. Tell me what you get. Sorry. Samuel, did you get a number?
I got I got my numbers. I got VA2 is -7,
Mhm.
VB2 is 0.02.
Very good. Very good. Okay, so with this collision, particle A completely changes direction. All right, it starts out moving to the right, it ends up moving to the left. Particle B starts out moving to the left, and it moves to the right a little bit afterwards. So they collide, and they go off in opposite directions to varying degrees. Okay, unfortunately, that's the easy part for today. Central impacts are much easier than oblique impact. Right, oblique impact will be the exam. All right, oblique impact. Let's talk about a diagram here. So we have two bodies where we realize that they are impacting each other. I'm going to draw the center of mass point G on these two bodies, which means that this is the line of impact, the line connecting the two centers of mass. Okay, but you can see before the impact, this VA1 and VB1, the velocities are not aligned with the line of impact, so this is what we call oblique. So today is, I've told you before that you can choose any direction of coordinate system that you would like, and you can still get the problem correct, But there are some choices that are better than others, some that are easier than others. Today is probably the first time that I'm going to more greatly encourage you to set the coordinate system the way I'm describing today. Okay? And the reason I'm telling you that is because there's a fairly formulaic way to handle these problems if and only if you set the coordinate system the way that I'm going to show you. Okay, so here, the way that it's shown in this problem is exactly the way that I want you to set up your coordinate system. I want you to put the x direction along the line of impact, and I want you to put the y direction along the plane of impact, that purple line that we drew in the very first diagram. Okay. So, if you draw the x and y directions as shown, this means that the impulsive forces act only in the x direction. Okay, so when we do this, when we put x along the line of impact, that means that the impulsive forces act purely in the x direction, which means I can tell you specifically how to handle equations for the x direction and specifically tell you how to handle equations in the y direction. But if you choose some other coordinate system tilted in some other way, I can't give you that direction as easily. Okay, so I need for you to set it up this way in order for my explanation to make any sense. All right, so then when we analyze these problems, we are going to handle the x direction and the y direction of motions separately. Okay, so let's talk about the x direction first. In the x direction. The beautiful thing yep, Braden.
Are we always going to be using Cartesian coordinates, or are we going to have to change our
For impact, we'll always use x and y. Yep, great question. Yep. Okay, in the x direction, the beautiful thing is that we treat the x direction almost exactly the same as central impact. Bless you. We essentially treat like central impact. And what I mean by that is that we, one, use momentum of the system is conserved along the line of impact so we can say that the sum of all the masses times velocities in the x direction at 1 equal the sum of all the masses times the velocity in the x direction at 2. What's the second thing we do?
Elasticity.
Yep, we use the coefficient of restitution to handle this issue of elasticity. So we use the coefficient momentum of each particle separately. Okay, so 1, we'll say that the momentum of particle A is conserved along the y-axis because no impulses act on A in this direction. There is an impulsive force on A. There absolutely is. But that impulsive force is only in the x direction. It's not in the y direction. Okay? So, because we put our coordinate system the way that it is, we still can use the conservation of momentum for particle A on its own in the y direction. Okay? So, here's what this looks like. We'll say that MA VAY1 equals MA VAY2. All right, and we could essentially copy and paste this for particle B. So 2, particle or momentum of particle B is conserved along the y-axis because no impulses act on B in this direction, meaning that we get this final equation. MB VBY1 equals MB VBY2. Yes?
I don't totally understand what you mean by like setting up the coordinate system that way. Is it just so the kind of directions in motion are at like a 45-degree angle between the axes?
No, it has nothing to do with the direction of motion. It has everything to do with the direction of the impulse. Okay? The impulse, the impulsive force that happens as a result of two things running into each other will always be in the direction of the line of impact.
So you just set that.
I set that as a coordinate direction so that the impulse is purely in that direction. Okay? Does that help at all?
Yeah, that makes sense.
Okay. Yep. Who was it that said at one point they were interested in billiards? Someone said they were interested. Anyway, we're going to start doing pool pool-like problems using this. Okay, all right, let's do an example. All right, we have a ball. The ball strikes the smooth wall with a velocity of VB1 equals 20 meters per second, as shown in the image. If the coefficient of restitution between the wall and the ball is E equals 0.75, determine the velocity of the ball just after the impact. Okay, so here they're saying B is the ball, which means that our other object, A, is the wall. So this is actually a little bit of an interesting case. So if we had, instead of doing a ball and then an immovable wall or a ball and a ground problem, if we, Caesar.
For the oblique impact thing, so how is the momentum of the system being conserved in the x direction different if from the y direction, if momentum of particle A and momentum of particle B are conserved, and particle A and B are the whole system?
Can you say that again?
Yeah. So for oblique impacts in the y direction, you said that momentum of particle A is conserved.
Yeah.
And also momentum of particle B is conserved.
Yes.
For the x direction, you said that momentum of the system is conserved.
Yes.
So how is that different if particle A and particle B are the whole system?
So if we were to look at particle A and particle B separately in the x direction, momentum would not be conserved in the x direction for each of those particles separately, right? Because that's the direction where the impulse due to collision is happening.
So it's only conserved as a system.
Sorry?
So it's only conserved as a system.
It's only conserved as a system. Yes. Simply because those impulses cancel out for the system, but they don't cancel out for a single particle. Okay? So it's a trick. It's a nifty little clever trick. Okay, sorry. So going back to this problem, if we had done two particles hitting each other instead of a particle and a wall, then we would absolutely use this first equation for the x direction. It turns out, though, if you have a particle and a completely immovable body, like a wall or the earth or just something just astronomically larger than your particle, we don't really need to conserve momentum in the x direction. We can just use the coefficient of restitution. And the main reason is that we have an unknown fallout. When one of those bodies doesn't move before the collision and it doesn't move after the collision, we have one less unknown. So we don't need to use conservation of momentum. We can just use the coefficient of restitution. Okay, so doing a particle and wall problem is just a little bit simpler than doing two particles. So since we are looking at a particle and a wall, we do not need to use conservation of momentum of the system in the x direction. It turns out just the coefficient of restitution will suffice. Okay, so let me prove that to you by doing the math together. Okay, so we have, I'm going to draw out or diagram out our system to begin with. So the plane of impact is going to end up being the wall, and the line of impact will be 90 degrees from the wall. Which means that I'm going to want to put my coordinate system as x, y. Now, I can absolutely see why this would be a tripping point for you, because how the heck did I decide that the center of mass of the wall is right there? I don't really know where the center of mass of the wall is. So when I'm drawing the line of impact, it's not really drawing the line between the two centers of masses anymore. What I'm doing is I'm thinking a little bit more carefully about what's going to be impulsive in this reaction. And it's the normal force that is going to skyrocket when this ball hits it, right? It's going to come into contact with the wall, and that normal force is just going to get really big. So that's our impulse due to this collision, and that normal force is normal to the wall, okay? So that's how I know that my line of impact is perpendicular to the wall, okay? All right, so I set my x and my y direction so that I can follow Dr. Higgins's formula for what to do next. So let's look at just the x direction. So I said we don't really need to conserve momentum of the system because we're looking at a wall. We really can just do the coefficient of restitution. So let's do that. I have E equals 0.75, which is equal to, we can go back up and say, oh, x direction, I need to grab this equation for coefficient of restitution. Okay, so what do I know here? I know, what do I know about particle A? Bless you. Caesar? It doesn't move, okay? So velocity of particle A after the impact is 0, velocity of particle A before the impact is 0. Do I know the velocity of particle B before the impact? I do, yes. It's given to me as 20 meters per second at this angle 30 degrees from the horizontal. Okay, so I cannot just plug in this 20 meters per second. I need to plug in only the component of this velocity going in the x direction, which is what? $20 cosine 30. 20 cosine 30 degrees. I don't know what happens to this thing after the collision. I don't know what's happening there. Question?
That piece negative still. Because it's like minus VBX1.
Yes, thank you. Yes. Yep. Okay, so we can actually immediately solve for the velocity in the x direction after the collision. So we should get that VBX2 is equal to minus 12.99 meters per second in the i-hat direction if you want. Okay, and then we can look at the y direction. So why did that not completely solve my problem? It asked for the velocity of the ball just after impact. That's a velocity of the ball just after impact. But it's only one component of the velocity, right? So this ball very likely has some amount of velocity also going in the y direction. So we need to figure out what that component is as well. Oh, goodness. Okay, y direction. All right, let's look back up at our notes. In the y direction, I want to consider the conservation of momentum for a single particle before and after collision. Which particle do you think is going to tell me the most here? The ball or the wall? The ball, right? If we do this conservation of momentum for the wall, what's it going to tell us? The velocity and before and after is both 0. So it doesn't really tell us anything. So in the y direction, I want to do conservation of momentum for particle B, specifically in the y direction. In the y direction. Because the y direction is the only direction for which it is conserved. Okay, so this says MB VBY1 equals MB VBY2. The mass of the ball. Well, does the mass of the ball matter? No, I've got a mass on either side. Okay, and in fact, this tells me that the velocity in the y direction before impact equals the velocity in the y direction after impact. The impact doesn't change it at all. Only in that direction. So we still need to figure out what is the component of the original velocity that goes in the y direction. Well, I sure hope it is a sine 30. Otherwise, we're in trouble. So 20 sine 30 degrees, and we're moving upwards in the y direction. So this is positive equals VBY2. And if we plug that in our calculator, we should get 10 meters per second. Positive j hat direction. So the total velocity is, we just need to plug those two components together. So I get minus 12.99 I plus 10 j meters per second. Okay, this is one of the more complicated days of this class. A lot of this is really just memorizing this formulaic set of what do I use in one direction, what do I use in the other direction. And I've tried to make that as step by step as possible. Okay, so what is the very first thing that we did? Well, the very first thing I hope that you recognize that I did is I drew the line of impact and the plane of impact, and I classified what type of impact are we doing. I did the same thing for this one. I drew the line of impact, I drew the velocities, and I decided this was a central collision. For here, we identified an oblique collision. On an exam, you're not going to know in advance what type of collision it is, so you have to be confident enough to be able to classify it. Okay?
Will you be looking for the line of impact on the exam? Is that kind of like a free body diagram you're going to want us to draw?
Yes, yeah.
Good to know.
Yeah. It's a lot like drawing your coordinate system. I can't tell exactly whether you understood the line, like the impulsive force direction, if you don't draw it.
Can multiple points for writing oblique or central?
No, but they will lead to doing the problem correctly. Yeah. So if it was an oblique collision and you start only doing the central collision steps, then I'll be like, hey, you didn't realize that this was oblique. Yep. Okay, so I classified the type of collision, and then I went back to my set of rules. What do I do for a central collision? What do I do for an oblique collision? For central, it's only one direction. I only have to look in the direction of the line of impact. For oblique, I need to do separate steps for the line of impact direction and the perpendicular direction, which if you set your coordinate system correctly, that'll be the X and the Y direction. Okay? Here, and here. Yes, Braden.
If the wall isn't exactly like perpendicular or vertical and there's like some sort of tilt to it and an angle 2 is not equal to angle 1, how do you solve that?
Angle 2 was not equal to angle 1 here. We never assumed that. And in fact, if you find this angle, the angle that this velocity makes with the vertical, it's probably not 30.
37.
So it doesn't matter. And so with that said, you can like look at this picture any way you want, as long as you realize that the normal force is perpendicular to the wall, and that is your line of impact direction, you're good. Okay, back in the back.
Do we have to know why the coefficient of restitution is only using X? No, that.
So the coefficient of restitution is extremely tightly coupled to the impulsive direction, right? The only direction where the force is going to be high enough that it causes a deformation of this body is going to be the direction of the impulsive force. And that impulsive force is the direction of this collision happening, the line of impact, okay? In the other direction, there are no impulsive forces happening, right? So there's not enough force to be causing this like squeezing and unsqueezing of this object. Does that make sense? Okay.
For the X direction, why do you cancel out VAX2 and VAX1?
Because the wall has no velocity before impact, and the wall has no velocity after impact. Yes.
The drop ball, like toss ball and angle downwards.
Yes.
Would you set down as like, would you use that for E? Because that's where the force is like squishing the ball down.
You talking about like I take a ball like this and I bounce it off the ground?
Yeah.
The direction normal to the ground
Yeah.
is your line of impact.
Okay.
Did that answer? Okay. Anything else? This one's just got some memorization to it. I'm sorry, but it does. All right, anything else? If you did not watch last class, please go watch that video for last class. Also, Thursday I'm going to move to Zoom. Thursday's class will be on Zoom. I will send out a Canvas announcement with that Zoom link, but it will be at the exact same time. It just won't be in this room. It'll be over Zoom. Okay? Question? There will be recitation tomorrow. Very good question.
So you won't ask us for the data, the final data?
I could.
You could.
You just calculate it from the velocity.
I just got it wrong, so I just tried it. And got
Compare
it
with Annabelle. I haven't done it, but
Maybe Annabelle got it wrong.
I haven't gotten it.
Maybe you got it right, Sam.
wrong. I got like 52. So.